In lecture 39 of our series on numerical methods in civil engineering, we will continue with our discussion on integral equations. In the last lecture, we looked at the two main classes of integral equations. We looked at Fredholm equations and we looked at Volterra equations, and we will also looked at Fredholm equations of the first kind and Fredholm equations of the second kind, as well as Volterra equations of the first kind and Volterra equations of the second kind. Today we will concentrate on homogeneous Fredholm equations, and the reason why we will spend some time discussing solutions to the homogeneous Fredholm equations is because these solutions, particularly these eigenvalues and eigenfunctions of these Fredholm equations, turns out they are very useful, and they are very useful in solving general integral equations. So, we will concentrate on the homogeneous solution, because the solution of the homogeneous problem helps us in solving the general non-homogeneous problem. So, what is a homogeneous Fredholm equation? A homogeneous Fredholm equation, recall, is of this form, plus on the right hand side there is a forcing function f of x. Now, if f of x is equal to 0, the integral equation becomes a homogeneous integral equation, in this case a homogeneous Fredholm equation. And we will first consider the case when we have our kernel to this Fredholm equation k of x of xi. It possesses symmetry, it is symmetric, and moreover it gives real values. For all values of x and xi, k of x of xi gives me a real value, right. So, it is a real kernel and it is symmetric. In addition, we will look at both situations where the kernel is separable, as well as when the situation arises when the kernel is not separable, right. We will focus on separable kernels first. They are separable, meaning that k of x of xi can be written as a function of x, as the product of a function of x and a function of xi, right. So, it is a separable kernel. So, the dependence of x and xi, of kx and xi on x and xi, can be separated out in terms of a dependence on a function of x and a function of xi, right. And why will we focus on separable kernels first? Well, principally because these separable kernels, they give rise to a finite number of eigenvalues and eigenfunctions. So, Fredholm equation with a separable kernel has a finite number of characteristic values and a finite number of characteristic functions, number one. And number two, that the insight we gain at looking at these separable kernels will help us solve the non-separable kernels. It becomes much easier to understand the non-separable case. So, a kernel is separable in x and xi when we can split it up into the dependence on x and xi can be separated out. That is, when kx of xi can be written as the sum of n number of terms of this type, where this is a function of x and fn is a function of x and gn is the function of xi. So, this is a separable kernel, in which case the number of it possesses, the integral equation possesses a finite number of eigenvalues and eigenfunctions. If it is not separable in x and xi, it possesses an infinite number of characteristic values and an infinite number of characteristic functions. Now, as I said, why do we concern ourselves with integral equations with separable kernels? Well, because they give us insight into the general problem. But we should remember, it is important to point out that in most real world problems, when do we get integral equations? As a result of some sort of modeling, right. And that model, when we do some modeling of a physical problem, we generally do not end up with an integral equation with a separable kernel most of the times, right. Most of the times it is not possible to write out our kernel as sigma n is equal to 1 to n fn of x gn of xi to separate out the dependence on x and xi. But still we focus on this case because it is simple. First of all, it simplifies things a lot. Number two, it gives us some insight into the general problem. So, if the kernel is separable, you can see that we can write the homogeneous Fredholm equation in this form, where all I have done is I have replaced the kernel k of x of xi in terms of the summation of these products of these functions of x and xi, right. And then we regroup terms. I pull out the dependence on x outside the integral and leave the dependence of xi inside the integral. So, gn xi y xi, I pull it inside the integral, and you can see then I have a series which is a function in x times this thing, which if I once it integrates out, it becomes a constant, right. It becomes a constant, and if I denote these constants as C1, C2 through Cn, basically I denote each of these integrals a to b gn xi y xi d xi as a Cn, then I can write this integral equation as y of x is equal to lambda times sigma n is equal to 1 to n fn of x Cn, right, where Cn is the constant I get after evaluating this integral. So, and if somehow we can determine these unknown constants C1 through Cn, you can see that I have a solution of my homogeneous Fredholm equation, because I know my fn of x. If I know my Cn's, I have solved I have got my y in terms of fn of x and Cn. So, that is the solution of my homogeneous Fredholm equation. So, how do we find out these Cn's? So, since there are n constants Cn, we obviously need n equations to evaluate those n constants, and we do that by multiplying both sides of this equation. We multiply both sides of this equation successively with each of the g's, right. So, we multiply both sides of this equation first by g1 of x, we get one equation, and then I integrate over the limits a to b, right, and then I multiply that equation by g2, again I integrate over the limits a to b, and in this manner I do this n times and I end up with n equations. And so, we will see that, but let us first look at some notation. We denote integral of a to b gmx fn of x dx as alpha mn, right. We denote this as integral as alpha mn. So, basically we are looking at this equation and we are multiplying both sides say by g1 of x, and we will integrate between a to b. We multiply the right hand side by g1 of x, we are going to integrate between a to b. We will integrate g1 of x fn of x between a to b, right, and and that we are going to call alpha 1 g1 of x integral of g1 of x fn of x is going to give me alpha 1n, right. So, integral of gm of x fn of x dx is going to give me alpha mn, right. And if I do that, I end up with a system like this. First equation, integral of g1 of x y of x dx is equal to C1, right. That is C1, because the definitions of my C's is just this, right. So, C1 is equal to integral of g1 xi y xi d xi, and if I multiply both sides of this equation by g1 of x and integrate, I am going to get C1 on the left hand side. I am going to get C1 on the left hand side. So, I am going to get C1, and on the right hand side I have lambda integral of g1 of x f whatever it is f of x, and then I get, if it is f1 then I get alpha 1 1, right. If it is f2 I get alpha 1 2, if it is f3 integral of g1 x f3 of x, that is going to give me alpha 1 3, and so on and so forth until I get Cn alpha 1n. And similarly I do for all, I multiply it again with g2 and integrate between a to b, I get this equation, and finally I multiply by Gn of x, integrate between a to b, and I get this equation. And pulling all the terms to the left hand side, we can see if we look at the first equation. So, there is this C1 here and C1 here. So, I get 1 minus lambda alpha 1 1 C1. So, I get that term, and when I bring this term to the left hand side, I have minus lambda alpha 1 2 C2 minus lambda alpha 1 3 C3, and finally minus lambda alpha 1 in Cn is equal to 0, and do it for all the equations. I get n equations in terms of my n unknowns C1 through Cn, and I also have a coefficient matrix which can be written in this form. So, basically my coefficient matrix is 1 minus lambda alpha 1 1 minus lambda alpha 1 2 minus lambda alpha 1 3 minus lambda alpha 1 n. So, I can write it as the identity matrix minus lambda times the alpha matrix, right. So, the identity matrix minus lambda times the alpha matrix, which I have denoted by A here, right. So, I get in matrix vector notation, I get a system like this: I minus lambda A C is equal to 0, right. And you know that for this system to have non-trivial solutions, the requirement is that the coefficient matrix must have 0 determinant, right. It cannot have full rank. So, it has 0 determinant, and that means its rank cannot be full. That means if I have n, if I had n equations, that means its rank must be less than n. So, the rank R must be less than n, and if the rank of the matrix is R, right, then n, in that case n minus this is should be familiar to all of us, because we have looked at this, we have looked at linear systems in detail earlier on. So, if the rank is R, so n minus R of the coefficients can be assigned independently arbitrary values, and the remaining coefficients can be determined from them. The remaining C's can be determined from them. So, the values of lambda for which this determinant I minus lambda A, this coefficient matrix, its determinant becomes 0, are the characteristic values, and for each of those characteristic values, the corresponding non-trivial C vector, right, the non-trivial solution of this system, the corresponding C vector will give us the eigen functions, right. How will they give us the eigen functions? Well, they will give us the eigen function from this equation, right, because once we know the C's, we substitute those C's for that lambda and we get y, right. That y is the eigen function of the integral equation. So, if n minus r of the coefficients Cn can be assigned arbitrarily, then n minus r linearly independent eigenfunctions are obtained corresponding to the eigenvalue lambda k, and in that case the characteristic value lambda k has multiplicity n minus r, right. It has got so corresponding to that single eigenvalue lambda k, there are n minus r linearly independent eigenfunctions, right. So, it has a multiplicity n minus r, and as I just showed, for the eigenfunctions then will have the form y k of x is equal to lambda k sigma n equal to 1 to n Cn Fn of x, and it is clear that the eigenfunctions are known only up to the arbitrary constants that need to be assumed in order to solve that equation. Basically this equation, right. So, because since the determinant is 0, right, we cannot have unique solutions, right. So, we have to assume some of the constants, right, some of the constants have to be assumed. The other constants C are evaluated in terms of those constants, right. If we have to assume the values of n minus r constants. If we have to assume n minus r constants, then n minus r constants can be assigned arbitrary values, right? They can be assigned arbitrarily. The remaining r constants are evaluated in terms of those n minus r constants, right? So, that means these eigenfunctions are known only up to the arbitrary constants that need to be assumed in order to solve my characteristic equation, right? In order to solve my characteristic equation and this equation, basically this equation, the characteristic equation would be determinant of that, but to solve this equation, that the number of arbitrary constants that need to be assumed is going to that would lead to the that would lead to the eigenfunctions being known only up to certain number of arbitrary constants, right? So, we have to assume those values of those arbitrary constants in order to get those eigenfunctions. But what is important is that even when I have these arbitrary constants, even when I have multiplicity say n minus r, it is possible. So, what did we see? We saw that for lambda k, if I have n minus r arbitrary constants, right, that means I have n minus r linearly independent eigenvectors corresponding to lambda k. But even if they are linearly independent, but we can make them orthogonal to each other. How can we make them orthogonal to each other? Well, remember the Gram-Schmidt orthogonalization procedure, which we looked at when we were looking at systems of equations, when we said that if you have say n minus r linearly independent vectors, it is always possible to come up with it is always possible to orthogonalize them, right? How did we orthogonalize them? We took a first vector, right? When it came to finding the second vector, we projected out the component of the first vector from the second vector, right? And we made sure that the second vector was orthogonal to the first vector. That is called Gram-Schmidt orthogonalization, and we use that for vectors. It is possible to do the same thing for functions, right? So, we start with our eigenfunction, we assume a certain we start with a certain eigenfunction, one of the linearly independent eigenfunctions. The next eigenfunction, we project out the part which we have already assumed, right? So, the next eigenfunction, we make sure that it is orthogonal to the first eigenfunction, and we proceed in this way, so that eventually we end up with n minus r not only linearly independent, but actually orthogonal eigenfunctions. So, they can be orthogonalized using a Gram-Schmidt type procedure. So, in general, so it is possible finally to end up with for n orthogonal eigenfunctions, right? It is possible to end up with n orthogonal eigenfunctions, right? We know that if we have multiplicity more than 1, those eigenfunctions are going to be linearly independent, but then we can orthogonalize them, right? We can orthogonalize them using a Gram-Schmidt's procedure. So, eventually for an n by n system, it is possible to end up with n orthogonal eigenfunctions. So, thus the characteristic value lambda k with multiplicity n minus r can be associated with n minus r orthogonal characteristic functions. So, up till now we have dealt with the theory, but I think some of the theory will become clear if we look at a specific example, right? And the specific example we are going to look at is going to be a second or a homogeneous Fredholm equation with a separable kernel, and it is going to be of type 2, right? It is going to be of type 2, y x is equal to, so you can see this kernel is y 1 minus 2 x I. It can be written in as a separable kernel, right? It can be written as a term 1 minus 2 x I. So, 1 I can think of that as comprising a function f1 and a g1, right? f1 times g1 with both equal to 1, that is going to give me the first term 1, and the second term is going, if I consider the x dependence to be equal to minus 2x, and the xi dependence to be xi. So, I have minus 2x xi. So, that is the second part of the kernel, right. So, that fits the form which we showed earlier on. Basically, it is of this form, right. So, n is equal to 2 now, f1 is equal to 1, g1 is equal to 1, f2 is equal to minus 2x, g2 is equal to xi, right. So, that is a homogeneous Fredholm equation with a separable kernel, and then we evaluate our C1 and C2. Recall that C1 is nothing but integral of g1 xi with y xi over that interval, and C2 is nothing but g2 integral of g2 xi with y xi. So, C1 gives me integral of 1 with y xi, C2 gives me integral of xi with y xi evaluated over the limits 0 to 1, and therefore, I get yx is equal to lambda C1 minus 2x C2, right, because remember we can write our equation in this form, right. C1 f1x lambda 1 C1 lambda C1x, right. Basically this is the form, right, lambda sigma lambda f1 C1 plus lambda f2 C2. So, we can write it like this, right, lambda C1 minus twice x C2. And again we want to determine C1 and C2. So, what do? We multiply the left, take this equation, multiply first by g1, right, integrate it within the limit 0 to 1. Next, we multiply both sides by g2, integrate the limits, integrate again over 0 to 1. If we do it with 1, we get this equation, and if we do it with x and integrate with over 0 to 1, we get that equation, right. You can see this x square term is going to give me x cube. So, that is going to, after integration, it is going to give me x cube. So, there you have that 3 here, and C1x, if you integrate, that is going to give me a square term. If I integrate between 0 to 1, I will get a half here, right. And if I integrate with if I multiply with 1 and integrate, so that is going to give me x, and 0 to 1, so that gives me 1. Here if I multiply with 1 and integrate, that is going to give me x square by 2, 2 cancels out. So, I have minus C2, right. So, this is what I get after multiplying first with g1 of g1 and then with g2 and integrating between 0 to 1. So, I finally end up with a system like this. It's a 2 by 2 system. Again, for it to have non-trivial solutions, the determinant of that coefficient matrix must vanish. That gives me my characteristic equation for lambda, right. I solve for lambda, it's a quadratic, so I can easily solve it, and I get lambda in this case equal to minus 3.6457 and 1.6457. If I substitute lambda is equal to minus 3.6457 in this equation, I get these two equations, and it is clear that these two equations are actually identical, have to be, right, because the determinant is 0. So, they are linearly dependent. These two equations are linearly dependent, they are identical, and all they tell me is that C2 can be written in terms of C1. C2 is equal to 1.274 C1. C2 is equal to 1.274 C1, and this therefore gives me, if I put C2 is equal to 1.274 C1 in this equation, I get my eigen function, which is y of x is equal to some constant a times 1.2548x. You can see there is a constant, because I am writing C2 in terms of C1, right. C1 still stays there, right. So, there is one constant there, right, you can see that, right, because here the rank is 1, right. So, n minus r is 1. So, I have to assume one constant value in order to know both my in order to evaluate both my C's, right. So, I have to assume one of them to be some arbitrary value. So, the eigenfunction is now known up to a single arbitrary constant. It is known up to a single arbitrary constant because my rank is 1. So, n minus r is equal to 1, and I know that it is known up to n minus r arbitrary constants. In this case, it is known up to 1 arbitrary constant, right. And so, this is the characteristic function corresponding to lambda is equal to minus 3.6457. Similarly, I can evaluate for lambda is equal to 1.6457, this equation gives me this system. If I solve this, I can get C2 in terms of C1 like this, and again I get my eigenfunction in terms of another arbitrary constant, and this is my eigenfunction. So, again I know the eigenfunction up to single arbitrary constant, and this is the eigenfunction corresponding to lambda is equal to 1.6457. For non-separable, so this was for separable kernels. For non-separable kernels, instead of having a finite, so you can see that in this case, since I could separate out my kernel into two products of x and xi, f1 x g1 xi plus f2 x g2 xi, I got two eigenfunctions corresponding to two eigenvalues, right, two characteristic functions corresponding to two characteristic values. In case I cannot separate it out, in that case I have infinitely many eigenfunctions and infinitely many eigenvalues, right. So, in case for non-separable but real and symmetric kernels, there are infinitely many eigenfunctions, characteristic functions defined with an arbitrary coefficient corresponding to the different characteristic values, right. This need not be one arbitrary coefficient. Depending on the rank, there can be n minus r arbitrary coefficients, right, since we are looking at. Okay. So, these characteristic values and characteristic functions of course are solutions of this system, because that is by definition, right. So, the characteristic values and these characteristic values, the characteristic functions, they must satisfy this system. And it turns out that if ym and yn are characteristic functions corresponding to two different characteristic values lambda n and lambda n, it turns out that if my kernel is symmetric, then these eigenfunctions are orthogonal to each other in the interval a to b. Remember that for my system of equations, my eigenfunction, for a symmetric coefficient matrix, my eigenvectors were orthogonal to each other, right, they were orthogonal to each other. Similarly here, even if I have infinite number of eigenfunctions, so long as my kernel is symmetric, my eigenfunctions are going to be always orthogonal to each other, and we can show that quite easily. So, suppose we have two eigenfunctions lambda m and lambda n, two eigenfunctions ym and yn corresponding to two eigenvalues lambda m and lambda n. That means they satisfy these two equations, right. Ym and lambda m satisfy this equation, while yn and lambda n satisfy this equation. So, we multiply the first equation yn of x with yn of x, that is with this eigenfunction, and then again integrate it over a to b. And similarly, we multiply this second equation with ym of x and integrate it over a to b. So, what do I get? For this equation, I have on the left hand side integral of a to b ym of x yn of x dx, and then here I have lambda m yn of x, this and then there is this integral a to b kx xi ym of xi d xi dx, right, because I am integrating now with respect to x, right, I am integrating with respect to x. Similarly, the second equation I multiply with ym of x and integrate with respect to x within the limits a to b. Let us look at this first, the first equation, basically this one. After we multiply with yn of x, I get this. Let me focus on this right hand side, and if I focus on that right hand side, what do I get? So, this is my right hand side, and then if I what am I doing? I am changing the order of the integration, because earlier I was integrating first with respect to xi and then I was integrating with respect to x. So, I change the order of integration. I integrate first with respect to x, kx xi yn x dx. You can see I have pulled yn inside, right, yn was outside, right, I have pulled that yn inside. So, I have kx xi yn x dx integral over a to b. I have ym xi. So, the integral over xi I have pushed it outside. I am first integrating with respect to x, then with respect to xi. So, I have this, but this is not really in the form of my integral equation, because this is kx xi yn x dx, right. If kx xi, but our actual integral equation was of the form where the second, the integrand, what we were respecting with what we were integrating with respect to, that was the second variable in the kernel, right, that was the second variable in the kernel. And if the kernel is symmetric, then k of x xi is equal to k of xi of x, otherwise not, right. But we have assumed that our kernel is symmetric. So, we can write k of x xi is equal to k of xi of x, because the function k is a symmetric function of xi and x. That is why I can interchange xi and x. If k were not a symmetric function of xi and x, I could not do that. If k of x and xi was x cube xi plus xi x cube plus xi square x plus xi x square, terms like that, it is not, it is, if it were not symmetric in x and xi, I could not have done that, right. Because I am assuming that it is symmetric in x and xi, I can write k of x of xi is equal to k of xi of x, right. And now that I have done that, it is in the form of my homogeneous integral equation, Fredholm integral equation of the second kind. So, this term within brackets is nothing but yn of x, right. It is nothing but yn of xi, right. It is nothing but yn of xi. If you look at the term within second brackets, that is nothing but yn of xi. So, I have in lambda m a to b ym of xi, yn of xi, and of course, I have to divide it by lambda n, right, because this term within this bracket is equal to yn of xi divided by lambda n, right. It is yn of xi divided by lambda n from the definition of my homogeneous problem, right, from the definition of my Eigen problem, right. So, this is equal to integral of ym xi yn xi d xi lambda m divided by lambda n, and this is equal to that. So, then this I can write it as, I can write it as lambda m minus lambda n, because this, you can see this integral is identical, right. This integral is identical. So, I can write it as lambda n minus lambda n integral a to b ym of x yn of x dx must be equal to 0. And since if my eigenvalues are distinct, that is lambda m is not equal to lambda n, after all I assumed that these are distinct eigenvalues corresponding to distinct eigenfunctions, right. So, if I do that, then lambda m cannot be equal to lambda n, which means that in order to satisfy this integral, y of m must be orthogonal to y of n over that interval a to b. Is that clear? So, distinct eigenvalues correspond to orthogonal eigenfunctions, right. So, similarly as in case of separable kernels, in case we have in case our eigenvalues have multiplicity greater than 1, if I have multiplicity greater than 1, then I know that if I have n minus r eigenfunctions corresponding to a particular eigenvalue, each of those eigenfunctions are going to be orthogonal to each other. They are going to be orthogonal to each other, and similarly I can again do a Gram-Schmidt type, sorry, they will be linearly independent, and I can again do a Gram-Schmidt type orthogonalization procedure to end up with n minus r orthogonal eigenfunctions. Is that clear? In case of separable kernels, in case a characteristic value has multiplicity greater than 1, then it has as many linearly independent eigenfunctions, and in such a case I can again orthogonalize using a Gram-Schmidt procedure. Thus, one can generalize that the eigenfunctions for a symmetric Fredholm integral equation are orthogonal. Symmetric Fredholm equation does not matter if the kernel is separable or not. Even if it is non-separable, we always end up with eigenfunctions which are orthogonal to each other. And it can, in addition, it can be shown that the characteristic values of a Fredholm equation with a real symmetric kernel are all real, right? They cannot be imaginary, they are all real. Remember, again very similar, it is very similar to our system of equations, right? For a symmetric matrix, for a symmetric matrix, we are assured that the eigenvalues are all real, right? The eigenvalues of a symmetric matrix are real. So, in this case, if I have a kernel which is symmetric, in addition, if the kernel by itself is real, right, the kernel by itself is not imaginary. So, if I have a real symmetric kernel, in that case my eigenvalues are always going to be real, right. My eigenvalues of my integral equation are always going to be real. That should be quite obvious, because let us go back and look at that equation. Suppose we look at something like this, right. So, if I have a real symmetric kernel, then if this is imaginary, it is certain that this has to be imaginary as well, right. This has to be, is that clear, right? If this is imaginary, let us go over it once more. If lambda n has an imaginary characteristic value, it is clear from the statement of the Eigen problem, since k of xi is real, then the corresponding function, eigenfunction, must be imaginary as well, right. Since this is real, if this is imaginary, right, then the eigenfunction has to be imaginary as well, right, because the right hand side, this is imaginary, right. So, it has to be imaginary as well, right. Is that clear? So, let us look at a situation where I have an imaginary eigenvalue, right. I have an imaginary eigenvalue, and I know that in that case my eigenfunctions got to be imaginary as well, right. My eigenfunction has got to be imaginary as well. So, I can write it in this form, right. So, alpha m plus IBM, that is my imaginary eigenvalue, and this is my imaginary eigenfunction, right. This is my imaginary eigenfunction. So, if I can write it like that, and then I group the real and the imaginary terms together, and I equate the real and imaginary parts, and if I do that, I get fm of x is equal to this, I get gm of x is equal to that, right. I can just by grouping the real and imaginary parts I get that, and then if I write fm minus I gm and I use these definitions of fm and gm in terms of alpha m beta m, then I'm pulling those terms together, I finally end up with something like this. And just by looking at this, what do you see? That corresponding to, so if fm plus igm is an eigenfunction corresponding to an eigenvalue alpha m plus I beta m, it means that fm minus igm is also an eigenfunction corresponding to an eigenvalue alpha m minus I beta m. So, if I have a complex eigenvalue, its complex conjugate is also an eigenvalue, and since for a complex eigenvalue I have seen that I must have a complex eigenfunction, that means that the complex conjugate of that eigenfunction is also the eigenfunction corresponding to that complex conjugate eigenvalue, right. So, so if lambda m and ym are complex eigenvalues and complex eigenfunctions, and the corresponding complex conjugates are lambda bar m and y bar m, the complex conjugates are also eigenvalues and eigenfunctions. We have just shown that, right. And recall that for distinct eigenvalues we have this condition, right. So, lambda m and lambda bar m are distinct eigenvalues because they are not equal, right. One is the complex conjugate of the other. So, I can always write that equation, right, that because I know that for any two distinct eigenvalues this condition has to be satisfied. So, this has to be satisfied for an eigenvalue and its complex conjugate as well, because I know that the complex conjugate of an eigenvalue is an eigenvalue also, right. So, this condition has to be satisfied, and then replacing lambda n and lambda bar m as well as ym and y bar m by their real and imaginary parts, which are this, right, alpha m plus I beta m and fm plus I gm in case of ym, we end up with an equation like this. And I know that both f of m, so this involves f of m square plus g of m square. So, the term within the first bracket there can only be 0 if both f of m and g of m are 0, right. But if both f of m and g of m are 0, that means my ym, which is equal to f of m plus I gm, has got to be 0, right. That is not true. Y of m is not equal to 0, that means this cannot be 0. So, the only way this can be 0 if is beta m is equal to 0. What does it mean? My eigenvalue was alpha m plus I beta m. So, beta m is equal to 0, meaning that the imaginary part is always going to be equal to 0. So, my eigenvalues are always going to be real. For a real symmetric kernel, I am always going to have real eigenvalues, right. This implies that a Fredholm integral equation with a real symmetric kernel must possess real eigenvalues. On the other hand, a Fredholm equation with a non-symmetric kernel may possess eigenvalues that are not real. That is certainly, that can happen, right. Non-symmetric kernel can always have eigenvalues which are not real. So, why do we spend so much time discussing the homogeneous problem, right? Why do we spend so much time discussing how to extract the eigenvalues and the eigenfunctions? Well, the reason is because it helps us, these eigenvalues and eigenfunctions, they help us find the solutions of the non-homogeneous problem as well, right? They help us find the solutions of the non-homogeneous problem as well. The usefulness of extracting the eigenvalues and eigenfunctions of a eigen results from this because of this following result, right. Any function f of x generated from a continuous function psi of x and a continuous real symmetric kernel k of xi. So, suppose I have any arbitrary function psi of x, the only requirement is that psi of x be a continuous function. And suppose I take the kernel and I take the product with psi of x and I integrate with a and b within the limits a and b, and I generate a function f of x. Then I am assured that in that case I can always represent f of x as a linear combination of the eigenfunctions of the homogeneous Fredholm integral equation with k of x I as this kernel. You know what is the homogeneous Fredholm integral equation, right? With the kernel k of x I, we know how to find its eigenvalues and eigenfunctions. It turns out that any function f of x which I can get by doing this integral, any function f of x which I can generate by performing this integral, I can represent this f of x as a linear combination of my eigenfunctions of my homogeneous Fredholm equation, and we will see its use in a few slides. In other words, it is always possible to write f of x as sigma n equal to 1 to n Cn yn of x, where yn of x is an eigenfunction of this homogeneous Fredholm equation. Remember, this f of x I generated completely arbitrarily, right? The only condition is that this function psi is a continuous function. It can be any arbitrary continuous function, it can be any arbitrary function. It may not have any relation with the eigenfunctions, right? It may not have any relation at all with the eigenfunctions. So, if I generate any function, if I take any arbitrary function of psi of x, I integrate it, I operate with that operate on it with the kernel kx of psi, right? Basically, when I say operate, I mean integrate it with over the limits a to b with take the product with kx and psi and integrate it, and I generate a function, right? That function I can always represent in terms of the as a linear combination of the eigenfunctions of this homogeneous Fredholm equation, right, which is a very, very important and very, very powerful result. Analogously, think about our linear system. What do we know? If I have a matrix, a symmetric matrix A, right, and I know that its eigenvectors are going to be orthogonal, what do I know? If I have a dimension n, then I know that the eigenvectors of A are going to form a orthogonal basis for the n dimensional vector space. That means any arbitrary vector of dimension n I can represent as a linear combination of those eigenvectors. So, similarly here, right, any arbitrary vector f of x which I obtain like this, I can represent as a linear combination of my eigenfunctions yn of x. Very, very important, but very, very similar to what happens in case of a linear system. So, this is very similar to the concept that any n dimensional vector can be represented by a linear combination of the eigenvectors of n by n symmetric matrix A, since these eigenvectors form an orthogonal basis, right. Okay. So, that is a very important result which we will use very soon, but at this point we digress and we mention that when we need to find, this sort of motivates why it is important to find the eigenvalues and eigenfunctions, because then we can use this very beautiful property of which allows us to represent any arbitrary function f of x generated by operating on the kernel, operating with the kernel on any function, continuous function. I can split it up in terms of the eigenfunctions, right. That is why it is very, very important to find the eigenfunctions. But we have seen that we can find the eigenfunctions for separable kernels. Yes, we can find the eigenfunctions relatively easily, but remember, what do we have to do to find the eigenfunctions? To find the eigenvalues, we have to solve this we have to solve, we have to evaluate determinant of I minus lambda A is equal to 0, right. And what is going to be the order of that equation? That is going to depend on the size of my matrix A. Since A was 2 by 2, it was 2 by 2, but if A is large, then that characteristic function is going to have higher powers of lambda. Since A was 2 in our example problem, we had a quadratic, there. If A is greater than 4, then if we know that we can only find the roots analytically only if it is 4th order or less, right. If it is 4th order or more, if my characteristic equation is 4th order or more, I cannot find analytic solutions, right. So, then what happens, right? Then I cannot solve it in closed form, right. I have to do it iteratively, right. I have to do it iteratively. So, I have to evaluate the eigenvalues and the eigenfunctions in an iterative fashion, right. And we will look at how to do that. Again, the way to do it is very similar. If you remember, we tried to, when we were talking about linear systems, we also looked at iterative methods to evaluate the eigenvalues and eigenfunctions, and we found that when we do that, when we do these iterations, we end up with we first find the largest eigenvalue and the corresponding eigenfunction, and then we can progressively find the next smallest eigenvalue, the corresponding eigenfunction, then the next smallest eigenvalue, and so on and so forth. So, doing a similar iterative procedure, it is possible to find the eigenvalues and eigenfunctions of a Fredholm integral equation as well, and we are going to do that in the next lecture. Once we do that, we will talk about how to use our eigenvalues and eigenfunctions to solve the non-homogeneous problem, and in whatever time is left, and because next lecture is probably our last lecture, we will look at some numerical methods for solving integral equations as well. Maybe we cannot do it in much detail, but we will at least introduce some numerical methods for solving integral equations. Thank you.